it on the on
Very good.
the it's real 1/4 inch plywood that I cut to
Oh,
the exact same size.
that was great. I have to do the similar things, hopefully, for my sessions. It was very helpful. Thank you for let us know on that.
You're welcome.
Hey, everybody.
Hi, Ekten.
All right. Give me a second to get set up here. What's new with everyone? Nothing.
I
Absolutely
had a
nothing.
question, Dan.
Okay.
If you want to observe an object that hasn't been proposed in the lab, how do you go determining the exposure rate for a particular object?
Right. Yeah. You're asking optical or radio?
Optical.
Okay. I don't have a good answer in either case. That's just me delaying, I guess. So in Skynet 2, we're building a rather elaborate and accurate exposure calculator that will take into account the efficiencies, throughputs of the systems. With each system, we measure, what's the current limiting magnitude that we're getting out of this telescope in the open filter? What are the ratios from open filter to all the other filters? And we use these calculations in Skynet 1. Like if you're in the generic telescope mode and you put in an exposure time, it calculates and you move your mouse over the other
Yeah.
telescopes, it says, oh, it's this much longer on this scope and this shorter, much shorter on this larger, better telescope. So we are doing those kinds of calculations. It's just not, it's not very good yet. And um, it's not exposed as a calculator in the website. It will be in Skynet 2.
Is there like a rough way of say I look up a magnitude of a particular object, I can estimate a exposure
Yeah.
roughly?
Yeah. So this is kind of based upon your experiences. What kinds of objects have you looked at so far? And like what magnitude are you talking about? Do you know?
Well, I was just looking at like this last set of galaxies in
Hmm.
the distance ladder, and I was like, well, I was kind of wondering about some other galaxies, and I wasn't really sure if there's a particular ratio to try or anything like that.
Yeah, just try different things. So
Okay.
kind of Messier targets. I mean, they vary, of course.
Yeah.
Like big bright galaxies, uh, like the ones in this lab. What were the exposure times? 60 seconds?
I think they were like
80?
80
80
seconds.
seconds? Yeah, that's a good exposure time for big bright galaxies. If you want fainter, if it's so every 5 magnitudes is a factor of 100.
Yes.
Every 2.5 magnitudes is a factor of 10. So if you're looking at a galaxy that's 2.5 magnitudes fainter, you probably want to expose 10 times as long to do
Okay.
similarly as well.
Okay.
Not great, but hopefully the tools we provide in 2.0 will be a little bit better.
Okay.
All right, let's see here. So I'm going to try to wrap up a little bit early because if I don't reconcile my university travel card by 5 p.m., they close it down. So I put it off to the last minute, but we'll see how quickly we can get through this. Okay, so we're almost done. We've worked our way up to lab 8. So we're getting into the tail end of the cosmic distance ladder. In lab 5, we started introducing standard candles, our Lyries, Cepheids, type 1As. Lab 6, we use them. Lab 7, we learned how to take spectra, radio spectra. Lab 8 is a concept lab to really understand the nature of the expansion of the universe, the Hubble expansion. And then we'll measure Hubble's constant in lab 9. And lab 9 will use distances and redshifts, and so it's kind of a capstone tying all this stuff together. Okay. So, check my notes here. Yeah, so Lab 8, it has a couple purposes here. One is to get us ready for Lab 9. You know, if you're going to measure the expansion of the universe, you need to understand the nature of the expansion. So it's a concept lab. It doesn't use Skynet, uses rubber bands, etc. And it's also a lab to cure misconception, kind of like Lab 2. And both of the two labs that don't use Skynet are designed around addressing common misconceptions. In Lab 2, we're trying to explain the nature of the seasons, why it's hotter in summer, colder in winter, which everyone famously always gets wrong. And as I mentioned before, I think we obsess on that topic because there are all sorts of things that people confuse and get wrong. And this is another example of that. So the Hubble expansion, the name of the theory is problematic. Big Bang Theory. You know, the name was given by Hoyle, who was a detractor of the Big Bang Theory. And so he's kind of mocking it. And the name stuck, and it creates this perception that in the beginning, space was there, vast and empty, and all the matter was at a single spot, and then boom, explosion, and it zoomed out, filling the space. And that's not at all what the Big Bang Theory is. That never was what the Big Bang Theory is. But that's the perception most people have of it. And so this lab is designed to kind of rectify that. Okay, so let's see where we are here. Let's go to the lab. So at the top of the lab, we have our standard videos. So we have 4 overview videos this time: the standard introduction, the background, the procedure. The background, there's a lot in the background. So, you know, if you're doing a lecture course, hopefully you cover some of these fundamental topics in your lecture. If not, you know, you'll have to hit the background as part of your pre-lab. The procedure, we'll get to that. And then we have an extra video on the equipment. And we talked about the equipment last time, but I'll review that in a second when we get there. And then there's just one how-to video on how to make a certain kind of plot, and that's embedded in the labs. Okay. So back here. Then we have the observing guide, placing our observations for Lab 9. So let's hop to Lab 9 briefly. And so this lab is relatively new. It's only been coded up in WebAssign this year. We had a paper copy for a semester or so before that, and we didn't have a Lab 9 before that, the capstone lab. We were going to try to do the Hubble's constant measurement using gravitational wave events. And we built a whole gravitational wave tool, and that actually landed in the MWU curriculum. When we realized that we could measure redshifts of galaxies with our radio telescope, then the plan shifted, and Lab 9 became more of a classical cosmic distance ladder exercise. But anyway, in Lab 9, we're measuring. So if you're measuring Hubble's constant, you know, there are 2 things: there are distances and redshifts. And the easy part's the redshift. You get that from spectroscopy. The hard part's the distance. And they've learned how to measure distances with Cepheids and type 1As. We're not going to make them redo that part, the hard part, but they will exercise their Lab 7 learned spectroscopy skills here. And so if we hop down to the procedure, we're going to be collecting more radio spectra of their 5 targets here. So these are galaxies that we can measure a redshift within, I think it's a 2-minute observation, 1 minute on, 1 minute off source. It's an on-off spectrum. In Lab 7, you know, we just pointed the telescope, brought in 5-10 seconds of data. The hydrogen line was whopping strong because we're looking at the Milky Way. We're in the Milky Way, but now we're looking at hydrogen for more distant galaxies. And in MWU, there's a whole bunch that we do, and we do longer exposure times and go fainter. But here in OPIS, we're trying to keep everyone on their time budget. So there are basically 5 galaxies you can do this with, where they're not Virgo cluster galaxies. And any galaxy in the Virgo cluster has a lot of additional velocities. You know, other galaxies are tugging on it, giving it a big Doppler effect, and that's not what we're looking for here. We're looking for the cosmological redshift. So I tested a whole bunch, and this is what we ended up with. So 5 galaxies, and each student will pick one of the 5. Okay. So to put the observation in, it's described here, but I'll just go to Skynet and we'll submit the observation. So here's the home page, observatory, radio observing. I'm going to add a new observation. One of those is the Sculptor Galaxy, NGC 253. I'll demo on that one. Search. Okay, I have it set to Green Bank. Here's now. Let's see, there it is. Yeah, this one's pretty low in the sky, Green Bank. And this is the Silver Dollar Galaxy, big bright galaxy. Let's see, so it's put in the coordinates. Minimum sun separation, 10 is a good number. You can do, of course, radio astronomy during the day, but if you're too close to the sun, it starts bouncing off the support struts and can mess up observations. Minimum target elevation, because this one is so far south, we recommend changing that down to 15. Here's 10, here's 20, so it's definitely above 20 degrees. But if you go down, if you lower this to 15, gives you a longer window, makes it easier to acquire these observations. You can see here the window is now 4, 5, 6 hours long. Save and continue. Here we are on the receiver page. The lab says to use the default. No, it says use the default 1406.25. Yep, and 1421.88. Again, we're in the high resolution mode, which you need to do the H1's 21 centimeter spectral line measurement. And you get these 2 spectra back to back, each of width 15.625. The line will be in this one up here. So they can just stay on the default values, but make sure they're in high res mode, not low res. Low res is good for making maps. Save and continue. Pick an account with some credits in it. And the path type now is not tracking, but on off. So 60 seconds on, gonna shift over 2 degrees because the beam is 0.75 degrees. So we want to get it off the galaxy, but we don't want to go too far because this signal is really, really faint. And so the spectrum is dominated by instrumental variations, and you have to subtract them out and subtract out the Milky Way hydrogen just to see it. So you don't want to go too far because that changes the Milky Way hydrogen, but you want to go far enough that your beam is no longer on the source. So we'll save and continue and submit.
Hey Dan, quick question.
Yeah, please.
Yeah, sorry, I don't have the radio astronomy background, but when you say beam, is that equivalent like the field of view, the radio?
Okay, yeah. The blurring scale.
Got
So
it.
the angular resolution. Often we teach this equation for optical telescopes, and you get angular resolutions that's less than the atmospheric blurring. Like a 5-meter telescope at optical wavelengths, I forget what it is. It's like 0.05 arc seconds, a 20th of an arc second, something like that, well below the atmospheric blurring scale. So we kind of can just ignore it at the optical. But that equation, the blurring scale, it's proportional to the wavelength and inversely proportional to the diameter. And these telescopes are big. What's that?
So it sounds like it's like the PSF for radio.
Yeah, exactly. Yeah.
Got
Yeah, it's because the wavelengths are so big. Even though the scopes are big, the wavelengths are even bigger. And so in the radio, it's like me observing you all with my glasses off. Everything's blurred out by about a degree. So, okay. Here, I did one about a week or so ago on the same target for my TAs. And here you can see what you get. We'll talk about more next time. But here's the on spectrum. And you see the instrumental variations. Here's the Milky Way hydrogen. This little blip right here, and it's broadened because the galaxy's rotating. That's our signature. So you'd easily miss that and not be able to see it. Here's the off spectrum. So you see it's gone. And then what you do is you do on minus off, and then you divide by the off to flatten it. And it gets rid of most of the instrumental variation. That little signature, here it is. You see it's a double horn sig. Here you have incomplete Milky Way cancellation. Ignore that. But the double prong thing there is the spectral line stretched out because one side of the galaxy is coming towards us, one side away from us. So you often get this horn-shaped profile. And so that's what they'll be measuring. The middle of that, it's very far from 1420.4. So that is how we get the redshift. All right. So each student puts in one of those. And, from a single galaxy, you can't get a great Hubble constant measurement. Some will be as low as 40, some will be as high as like 110 or something. But if you average across the 5 galaxies, you get Hubble's constant of about 70, which is, right on. So that's pretty good. Anyway, back to the concept lab here. Okay. Check on my notes. Let's talk about the goals of the lab. So learn that the Big Bang was not an explosion in space, but an explosion of space. It's kind of a cutesy way to say it, but by that I mean a rapid expansion of space. So again, addressing the misconception that space wasn't just there. Students have a hard time coming to grasps with the idea that space is stretchy. So they just think space was there and you had this explosion in space. But, space was always full, uniformly filled with matter, even in the very beginning. It's space itself that is expanding. We'll try to convince them of that. The second goal is to determine that our galaxy is not the center of the universe and that the universe, in fact, has no center. So they're going to be making these Hubble law plots. And you know the Hubble law plot. In fact, here's an example. The farther away you go, the faster away things are moving. And it makes once you get this, and it's cool, we'll be able to derive it just from the stupid rubber band. But once you get it, you look at it and you say, oh, everything's moving away from us. We must be at the center of all things. And that would be a shame because the whole point of this whole lab sequence is for them to realize, going back to like lab 3, we learned Earth is not the center of the solar system. In lab 6, we learned the sun is not the center of the galaxy and the galaxy is not special. And then we get to the end here, we don't want them walking away with the wrong idea. And so they'll do this measurement from multiple galaxies on the rubber band, and basically every galaxy sees everything else moving away in this fashion. So that's the second goal, and show that we're not at the center and the universe, in fact, has no measurable center. And then the third one is we're going to do this for 3 types of universes. Decelerating, a universe that's expanding at a constant rate, and accelerating. And then we'll look at type 1a supernova data, basically Hubble's law curves in these different scenarios, just to jump ahead to the punchline. So here's, my mouse is kind of half broken. Redshift versus distance. These are some type 1a supernovae. There are many, many, many more of them now. And here, the one in the middle is the constant rate of expansion, but one of these is accelerating, one of these is decelerating. They'll figure out which, and then they look at this data and say, oh, we're on that one. I won't give away the punchline. We know it's accelerating. And so they're going to build up that. Basically, the thing that they're doing in this lab is figuring out which way Hubble's law curves for acceleration versus deceleration for that goal anyway. Okay, equipment. We talked about this at some length last time, but just to review very quickly. Rubber bands, not any rubber band. It has to be, 18 centimeters when cut or longer. But the standard size is 9 centimeters folded, 18 centimeters open. It has to be a little bit thick. You don't want a really thin rubber band because you're going to be putting push pins through it. scissors to cut the rubber band, a ruler with a centimeter scale. The rubber band will be stretched all the way out to 27 centimeters at most, which fits on a 1 foot ruler with a centimeter scale. Marker to mark your galaxies. We're going to put 5 galaxies in our one-dimensional universe, conveniently equally spaced, and stretch our universe. Push pins, and then something to stick it into. Foam board, cork board, cardboard, and sometimes you'll have to pull it over. Well, we'll get to the procedure part in a bit. So we talked about that last time. Those supplies, if you're teaching online, give the students enough time to find the supplies. If you're teaching in person, you should buy them for the class. You can buy these things in bulk fairly inexpensively. Okay, the background sections. We have 2 of them. So let me slide down to background in my notes. Okay, Hubble's law, as I said, and as we all know, it's a plot of distance on the x-axis and apparent recessional velocity or redshift. It can be done either way. Historically, they plot a velocity on the y-axis, a recessional velocity, how fast it's moving away, but I emphasize apparent because kind of that's one of the points of this lab. These are not moving through space at this speed. Space is expanding, stretching, carrying them with it. So it's an apparent recessional velocity. And so this ties back to other labs, as I was saying. Distances, we learned how to measure those in lab 5. Cepheids and type 1As get us out to these kinds of scales. And the recessional velocity, we get that from the spectrum, and we learned how to do that in lab 7. And for that, what they know so far is the non-relativistic Doppler equation right here, V equals C times Z, nice and easy to use. But keep in mind that is the Doppler equation. And Doppler equation is for motion through space. So we'll come back. And ultimately, these things should be plotted versus redshift for the reason I just said, that they're not moving through space. Space is carrying them. Okay. And what do we have here? So the farther out we look, faster everything is moving away from us, or appears to be moving away from us. There are exceptions. Like Andromeda is moving towards us, but Andromeda is in the local group or gravitationally bound, close enough that gravity wins over the Hubble expansion. The farther away you go, the stronger the Hubble flow is, but at close distances, it's not very strong. Like it's not pulling our atoms apart or anything like that. And within the local group, gravity wins. And so Andromeda is actually moving towards us. But everything else is moving away once you get outside the local group. You do see some scatter here. That's not measurement error. That scatter is real, and that's due to actual Doppler motions on top of this flow. These are galaxies. Each point is a galaxy, and they're being tugged on by other galaxies near close to them. So sometimes the velocity is enhanced or subtracted from around the overall Hubble flow. Now, let's imagine running time backwards. So the stuff that's far away is moving away fast, and the stuff that's nearby is moving away slow. If you ran the clock backwards, the stuff that's far away would be coming to us quickly. The stuff that's nearby would be coming to us slowly. As long as this is linear, that means everything is on top of everything else at a certain time in the past. And so the universe has a beginning. As soon as Hubble plotted this and saw the linear relationship, the direct inference is that time was not infinite. Whatever the cause of this is, just the mechanics of it, at some point in the past, everything was on top of everything else. And that's the start time. And then from there, if you run time forward, it feels like an explosion. Everything was on top of it, on top of everything else, and then it wasn't. It was expanding out. So you can see why people would get the misconception. But it is a misconception, and there are a number of ways that you can see this. Oh, and that time is 13 well, it's now 13.8. The CMB data had a minor update since I wrote this, 13.8 billion years. And basically the inverse of the slope of this line is the age of the universe, which is kind of cool. Okay, but why is it not an explosion from space, in space? So a couple reasons. First reason, and there are more reasons we don't even touch on in the lab, like there's cosmic microwave background related reasons. I'll mention one, but we save that for the next lab. Reason one is if it was an explosion in space, you would have an expanding shell, right? If everything exploded at the same velocity, it'd be a perfectly thin expanding shell. Now, if there's some distribution of velocities, it's a fuzzy shell, but certainly it has a hard outer edge because nothing can go faster than the speed of light. So everything out there would be completely empty. You'd have an overdensity and probably a hollow middle. So if it's an explosion in space, you have a shell-like structure. You would expect that. And we've looked out. Here's an example, a galaxy survey. These have been done in all 3 dimensions. This is just one slice going out on one side of the sky and a slice on the other side of the sky. And each point in here is a galaxy, which is it's worth emphasizing that with your students because there are a lot of points and just imagine each little dot is a galaxy like our Milky Way. It can be a mind-blowing concept. And if you look at it, you don't see shell-like structure. You do see some clumping. On small scales, it has clumped together. That's just due to natural gravitational attraction. On scales kind of this size that I'm moving my mouse over, the average, if you average the galaxies on that kind of scale, it's pretty uniform, homogeneous. The term is homogeneous. Now, if you keep going further and further out, it looks like the density drops off. But that's an observational effect. We see fewer galaxies far away because they're harder to detect. They're farther away, they're fainter, harder to detect. But we really understand the nature of our instruments, the sensitivity of our instruments. And once you correct for that, statistically, you can show that the density stays constant all the way out. The universe is homogeneous and it's isotropic, meaning same numbers in all directions. So there's no hard edge. If there's a hard edge to the distribution and we were close to it, we'd see fewer galaxies in that direction and more, into the main thing. And that's an assumption cosmologists have made ever since the beginning. Kind of theoretical heyday of the Big Bang Theory was the 60s. They just assumed homogeneity and isotropy. It simplifies all the equations, and that's now been confirmed by the galaxy surveys. The point is there's no big massive shell emerging, and it wouldn't be centered on us. We would be in the shell. You'd see kind of a big circle with us in it, and we just don't see that. I'll do this one in a second, but just to digress and give you one tied to the CMB that I don't do here. If there was, everything's on top of everything at some point, it would have been dense, hot, opaque. Those are the conditions for producing a thermal spectrum, which is what the CMB is. And then you run time forwards and the density drops to the point that it's no longer opaque, it's transparent, and that light is released in all directions. If everything started at a single point and the matter is expanding at some sublight speed, the CMB light would stream out at the speed of light, and it would go beyond our shell, and we're in the shell, and we wouldn't see any CMB. It would have streamed past us long ago. And of course, we do see the CMB. So there's another reason why, kind of related to the shell argument. But I don't talk about that one here. I saved the CMB for next time. It's a heavy of enough intellectual lift to wrap your mind around expanding space that we don't need to introduce the CMB on top of it here. But here's the second rebuttal to the common misconception. And it's a little bit of a cheat, but it's okay. So here's the Hubble Deep Field, thousands and thousands of galaxies. And in this picture, the redshifts the Z's have been labeled for some of them. They've been measured for like all of them, but just labeled on some of them here. And I circled the ones that are above 1. So if the redshift is above 1, given the equation they know, and this is the cheat, but I'll get there in a second, that would imply a speed above c. And if there's only one piece of modern physics they know, it's that you can't go faster than the speed of light. Yet here are galaxies with redshifts greater than one. And if this was an explosion in space, these galaxies would be moving away from us at speeds greater than the speed of light. And they know that's not allowed. So that's another reason why the exploding shell can't work. Now, I've never had a student smart enough to come up to me and say, well, this is the non-relativistic Doppler equation. If you're moving at light speeds or near light speeds, you need the relativistic Doppler equation. Now, I did cover my butt here and wrote a paragraph about that. It's true. This equation is not correct once you approach the speed of light. If you use the actual equation, which is more complex, you'll never get a speed greater than c. The closer, the height, if the redshift gets above 1, you end up with the speed not above c, but close to c. It doesn't actually break the laws of physics. However, if you're moving close to the speed of light, all sorts of other things happen. Time dilation. If you looked at variable stars in these galaxies, they'd be pulsing slowly. Length contraction in the direction of motion. We wouldn't see that since the motion's away from us. But relativistic mass, the masses would be higher, and we would see different gravitational effects compared to things in their surroundings. We don't see the time dilation or the relativistic mass. So even if someone's smart and realized, okay, there is actually a different equation, doesn't imply speeds greater than c, just speeds close to c, we still don't see any of those special relativistic effects. So it doesn't work in any case. It can't be an explosion in space. And again, the theorists never said it was. It's just the common misconception. So what is going on? If it's not motion through space, what are we looking at here? So the answer is the space itself can expand. And I have a couple examples here. There's one that's not in the lab. I have a figure. I'll pull that up in a second. I'll probably put it in the lab next time I edit this. So when Einstein laid down his equations, he showed that space itself is flexible, can expand and contract. Now, it's hard to visualize because space is three-dimensional. So expansions and contractions, and again, I apologize. I know you know these things, but as you'd present to a student, the expansions and contractions, you need a fourth dimension in which to visualize your three dimensions expanding. And we can't visualize 4 dimensions. So we have a couple of ways of approaching this. One is to go 1 dimension down. That's what we have here. We imagine space as a 2-dimensional sheet. So here's the Big Bang. With time, the sheet is expanding. These galaxies are not moving in space. Space is expanding, pulling them apart as if they were taped to a rubber sheet and we all grab the edges and pull. You look at any other galaxy, let's say you're the red one, all the other galaxies would appear to be moving away from you, but they're not actually moving through space. So that's the 2-dimensional way of thinking. If you want to try 3 dimensions, here's my favorite loaf of raisin bread because the raisins are perfectly symmetric. This was made by some master baker that placed the raisins on a perfect grid, which helps us to visualize this. So you put the raisin bread in the oven, it bakes, the bread expands, carrying each raisin away from every other raisin. Now, this one is not like the universe because it does have an edge. Inside that loaf, it is homogeneous. The raisins are distributed homogeneously, but not isotropically. Because if you're on the edge, you wouldn't see any out of the loaf, but you'd see a bunch into the loaf. So really, you need an infinitely large loaf of raisin bread for this. Now, I'll go on a little tangent here. I have a hard time with physical infinities. Infinity to me is a mathematical concept. I just can't believe that in the actual physical universe, it would be infinite. If I'm God creating the universe, it just seems so wasteful. If the universe is infinite, infinity is really big. It means that there's another group of the 6 of us having the same conversation, not just somewhere else in the universe, but an infinite number of times throughout the universe. It's one of Max Tegmark's 4 classes of multiverse. before you get into like the quantum mechanic-y multiverse. If you just have an infinitely large multi universe, everything's repeated an infinite number of times. So I personally don't like physical infinities. To me, it's more of a mathematical concept, but that's a tangent. Fortunately, Einstein provided for that as well. Since space is stretchable, it's also bendable. We know this locally around objects. Gravity in Einstein's theory is just a warping of space. It's not a force of nature, but a warping of space. And you can also have warpings on the scale of the universe itself. So again, we have to go one dimension down to visualize this. But here we have coins taped to a balloon. The surface of the balloon is the space. Inside the balloon is not the universe. Outside's not the universe, but it wraps around like the surface of the Earth wraps around on itself. Um, Now, in Einstein's equations, the universe doesn't have to do this. It could actually be infinite, but this would be a closed universe where it does do that. And so you go one dimension up, and it's then three-dimensional space that where you just travel off in one direction, you end up where you started after a long period of time, wondering how the hell that happened. But mathematically, you can have that. It'd be a finite amount of space. Stephen Hawking, we can't visualize four dimensions, but Stephen Hawking said that he pulled it off for about 15 minutes. He could visualize four dimensions, which makes me think of my college roommate who also said he could visualize four dimensions. He was high on pot at the time, which makes me wonder what Stephen Hawking was smoking. But anyway, that's my little. I use that joke every time I teach this to students. But okay, so we've established that the Big Bang is certainly not an explosion in space, and we have this alternative way of thinking about it that will verify with our stretchy rubber band that it's an explosion or rapid expansion of space. But there's still one more thing we have to resolve is if these things aren't moving through space, what's this redshift we're seeing? So far, the students only know about Doppler redshifts, which come from moving through space. Remember the diagram of the concentric circles, and if the object's moving, the circles get squished in one direction and stretched out. That's motion through space that creates that redshift. And if this is not motion through space, what is this redshift that we're seeing? And it's called a cosmological redshift. And basically, the way to think about this, slide down my notes, is a light wave has no internal cohesion. We take us, for example, we have internal cohesion. We have intermolecular bonds that hold us together. The forces between the molecules are strong enough to overcome the expansion of space. So space is expanding around us, but we stick together. As I said, the Hubble flow is strongest when you have large, at large distances. This is going up at large distances. At small distances, it's getting small. So forces can overcome it. So we don't expand with time. But you can make the standard also joke here at this point that, now that I'm getting older, I'm starting to expand, make jokes about expanding waistlines and whatnot. But anyway, the Earth, the gravitational attraction of the Earth is enough to hold it together against the expansion of space. And the same with the solar system and the Milky Way and our local group. As I said, with Andromeda, it's being pulled towards us. The gravity drops as 1 over distance squared. This thing increases with distance. So there'll naturally be a point where the Hubble flow wins and it's outside the local group. So all these things within the local group, we can hold ourselves together against the expansion, but light waves have no internal cohesion. That's kind of the simple way to explain this to a student. So as they travel across space, they just expand with the universe. And the wavelength gets stretched out, not due to motion, but just because it's traveling through expanding space. So by the time it gets to us, it's a longer wavelength, which is a redder wavelength. Now, I wouldn't go here, but it also is a lower frequency, so a lower energy. And kind of the great question that my students never ask me this question, but when I teach OLLI, Osher Lifelong Learning Institute, it's for seniors. I love teaching OLLI because they are not shy. It's not like your normal students who you can't get them to speak up or ask a question. You can't get the seniors to shut up, and they think really deeply. Particularly here, Research Triangle Park, they're all retired scientists and whatnot. So they ask, where's the energy go? All this light is being redshifted. The energy is decreasing. Where does it go? And I still don't have a good answer. I've read very deeply. General relativists say it's okay. It becomes part of the gravitational field of the universe, but it's all very hand wavy. Abbas, your hands up. Oh, his hands up, but he's frozen. Is he frozen for you guys too? Oh, you're back. Abbas, your hand is up.
Yes, I don't know. It's kind of things about regarding to your question about the arguing about the infinity. I have a similar thought about the singularity. I mean,
Yes.
are you think both of them mathematical concept? They
Yep.
are not actually in the physics available.
I fully agree. One over infinity is a singularity. And so I don't believe in physical singularities either. Uh, so the centers of black holes
Yeah, exactly.
and the Big Bang itself are the two singularities that we're most focused on. And those are the two and only two places where modern physics breaks. You know, I'm sure I've gone on my modern physics rant before, but we have our great two theories, quantum mechanics and general relativity. They've each passed every test. They're beautiful theories, but they're built on incompatible foundations. In one, everything has a well-defined position and well-defined momentum, general relativity. Quantum mechanics, the better you know one, the worse you know the other. And so the postulates are incompatible, and modern physics is built on this broken foundation. So something is wrong. One is wrong, the other is wrong, or they're both wrong, but they both work perfectly. So that's the big conundrum. Uh, and you can use them together, and they play nice together, except when you have a lot of mass in a quantum volume. And that's just, once you get down to singularities, like the centers of black holes in the Big Bang.
Thank
And
you.
yep. So you got me going on one of my favorite rants there. But I just to end it, I think once that's resolved, if someone ever figures that out, then we'll learn that those singularities are not mathematical singularities. There is some finite size limit down there. Something's got to be propping up the black hole on some scale, even if it's fundamental particle scales.
And yet, The Theory of Everything was a great movie.
I haven't seen that yet, but I'll take the
It's
recommendation.
it's interesting. But I posted a comment a few minutes ago when you were talking about the infinity. And it's like,
Oh yeah, go ahead, because I'm not looking at the comments.
the inverse of that, so to speak, is if the universe is not infinite, if there are limits to the universe, what is beyond the limits?
Yes. And so the only way that works, I think, is if it wraps around. You can't
Right.
Einstein's equations don't permit a hard end, no, an edge.
But
Where
does that not make it? Does not that not? If there's no end and no beginning, is that not like the definition of infinity, in a sense?
yes, though in a universe like this, there is a finite volume.
Right.
So yeah, you can loop around it forever, but it's not an infinite amount of space.
Okay.
Yeah.
It's just fun to. It's just like you said. It's you know Saturday midnight conversations in college.
Yes.
Fun to rehash. So.
And you can take advantage of this lab to have those kinds of conversations with your students because it's fun stuff.
Yeah, that's what makes this stuff, physics and particularly astronomy so intriguing, so fun.
We could have
I
just jumped right into Lab 9, measured Hubble's constant, but I think it's worth having this lab so you can have those kinds of deep thought discussions with your students.
I asked my son because I love to do this to my son. I'm like, okay, so if we put JWST or Hubble up there and we're looking backwards in the universe, can we turn it around and look forward?
Yeah.
He's like, I hate you.
Yeah.
Anyway, I digress.
Sure, sure. And so we're done with the background. There's a little review of the cosmic distance ladder, how we went from the Earth scales to Hubble scales. This is the ultimate tool. Right now, we just find any galaxy, measure its redshift, and we get a distance. But here it is plotted versus redshift, which is what's actually it should be plotted, not the Doppler interpreted redshift. Anyway, let's get into the procedure before we run out of time. Now, this lab, it's long enough that the last question was broken off. So you run into these situations like if I go to the end of this procedure, I can very easily miss this one and hop to that one. So be careful about that. Let me close this back up. So here's our rubber band universe. You take the rubber band, cut it open. Here you can see it's about 18 centimeters. You put dots at 3, 6, 9, 12, and 15. So 12 centimeters total with some space on the edges. You could practice pinning it into your board. You may have to pull the board over the edge of the table if the pins go all the way through it. That's okay. And then practice stretching it out to 27 centimeters between the first and last dots. That's the biggest stretch. When they do this, you probably want to put the push pin in at you have to put it in at an opposing angle, or else it could get dislodged and fly across the room. And as you know, it's all fun and games until someone loses an eye. I've actually bought safety goggles for my students now. So maybe you want to invest in that as well. Okay, let's get to the meat here. So Hubble's law. How are we going to measure Hubble's law from a rubber band? So the rubber band, the idea is it's a one-dimensional piece of the universe. I've stuck 5 galaxies on it. And they have godlike powers. They start at the resting position. They don't start at, the Big Bang would be the whole thing squished. I can't squish the rubber band. I have to start at this point here. So these early ones are grayed out because we can't unstretch the rubber band. But starting at the resting position of 12, that's the distance between galaxy 1 and 5. This corresponds to minute number 4 in my universe. They're going to do some measurements. And so with their godlike powers, they're going to stop time, pin it in, make their measurements, and then they can unpin it, restart time. They don't have to slowly expand it for the next minute out to 15. They can just make time run quick, stretch it out to 15 centimeters, pin it in, make their measurements, et cetera, et cetera. So they have godlike powers. They can stop time, start time, make measurements, et cetera. And so here we have the distance between galaxy 1 and 5 as a function of time. Even before they make any measurements, we have them plot up that distance versus time. This is just the first 2 columns of the table, nothing they measured. Just to see that, yes, this is a constant rate of expansion that we're doing right now. Okay, and then at each position, they're going to measure the distance from galaxy 1 to 2, 1 to 3, 1 to 4. They don't have to measure 1 to 5. They use that to pin the rubber band. And they fill out this table. And the smart ones realize they can interpolate, encourage them to actually make measurements instead of interpolation. Okay, now we need 2 things. We need luminosity distance for the x-axis and cosmological redshift for the y-axis. And we can get all of that from these measurements, which is kind of cool. It's really about 2 things. How far was the galaxy from us when it emitted the light, d then, and how far is it away now? And so the yellow boxes correspond approximately anyway to the granularity of this table, how far each of these galaxies was away when it emitted the light. In this universe, light has a certain speed in centimeters per minute that may not match the actual, but and then this is how far away the galaxy is now. We can't see it now. We can only see, what it looked like when it emitted the light. The light itself traveled something in between those 2. Okay, but those are the important things. So after they have their measurements, they're going to grab the D thens and put them here, grab the D nows and put them here. But the last one was set by the pins, but the other ones they measured. Then they're going to calculate 2 things, luminosity distance and redshift. So let's do luminosity distance first. The path that the light travels, I said, is It's longer than how far apart they were when the light was emitted, and it's shorter than how far apart they are now, something in between. The actual equation's complicated, depends on the cosmological parameters, omega matter, omega lambda, etc. For the accuracy of this lab, they can just average the two. That's close enough. They average the two, and that is an approximation for what we call the coordinate distance, not the luminosity distance, but the coordinate distance. If I could take a ruler and keep laying it end over end as that light ray was traveling across the universe from the galaxy to us, that's what the ruler would measure. But we can't do that. We don't have tape measures that we can stretch out into space. So we measure luminosity distance, standard candles. And there's an extra factor of 1 plus z, which in the language of d nows and d thens is an extra factor of d now over d then. D now is bigger than d then, and so luminosity distances are bigger than coordinate distances. So the first time I ran this lab, I didn't have this in here, and my Hubble laws were curved when they should have been straight. Then I realized, oh yeah, I'm doing coordinate distance. I need to do luminosity distance. I need to throw a correction in here. Physically, what's going on? Think of the light train as it's coming to us from the target. You have light, crests at a certain rate, and by the time it gets here, it's been stretched out by the expansion of the universe. So we receive those crests or the photons. If it's a sequence of photons, they may have been emitted like this, but we receive them more slowly. So to us, it's fainter, and which means we infer that it is farther. The luminosity distances always come in higher than what you would actually measure from a ruler. So it's a little tricky, but you have to have that correction factor. You can do it either way. You can say, okay, you got the coordinate distance, you need this correction factor, just use it. Or if you want to try to explain it, you got to talk about the light train being spread out, looks fainter, we infer it's farther. Anyway, you put this and this together, and they can turn each of those into a luminosity distance, and they put that here. That's your x-axis. For your y-axis, it's the cosmological redshift, which is delta lambda over lambda then, the emitted wavelength. And if these waves are just stretching with the universe, the wavelength is proportional to d now, d then. So instead of lambda now, you can imagine some constant times d now. Instead of lambda then, some constant times d then. The constants cancel. So d now minus d then, whole thing over d then is just the cosmological redshift. So again, kind of cool. Just from simple measurements on the rubber band, they can get luminosity distance and cosmological redshift, and they can plot them against each other. And here I did it with actual measurements. So again, idea of the scatter, something like this. It's linear. At least for a constantly expanding universe, it's linear. Luminosity distance here, redshift here. They use the basic plotting tool in the Astromancer suite, this first one for that. Basic question. Hubble's law states the farther a galaxy is from us, the faster it appears to be moving from us. Have you replicated Hubble's law? Yes. And so this weird thing, it's just weird that we look out and everything's moving away from us, and the farther away it is, the faster it's moving. That's weird. But now they've replicated it with very simple things, a rubber band and rulers. And so they can see it is due to the expansion of space. These dots are not moving on the rubber band. The rubber band is stretching, and that naturally gives us Hubble's law. They're going to do it 3 more times. As I said, you look at this, it looks like everything's moving away from us. We must be at the center. Again, we don't want them walking away with that. So in part C, again, don't miss it. It's easy to miss it because of how the lab was split. We have them do it again, but measure everything from the position of galaxy 2. And all the distances are positive. There's no negative distance in space. And in a 1D space, yeah, you could have a negative distance, but in the real space, all distances are positive. And if I don't have a note, I'll add a note to that effect. That's a mistake we sometimes see. So they redo the measurements from the second dot in the rubber band. Here's the first dot. I'll hold that in the middle of the camera. Everything appears to be moving from it. But if we focus on the second dot, everything's moving from it. The fourth dot, everything's moving from it. They should all get the same Hubble's law. And so they just do it again, get their D nows, D thens, calculate the stuff, and then they plot it using a different plotting tool I'll show you. But here's the result. We're in answer key mode, so they can't see the answers. But it lands right on top. You don't have that extra dot because we moved one dot in, so we don't have another dot that far away. But everyone in Galaxy 2 sees everything moving away from them, and the farther away, the faster it moves. Now, to plot this one, you can't use the curve tool. The curve tool lets you plot multiple curves, but they all assume the same X value. So instead, we have a tool down here called dual. Same idea, except you have a different X for each Y. And so we have them plot Hubble's law from Galaxy 1 and Hubble's law from Galaxy 2 on the same plot. And so they can see that, yeah. So questions, do the observers in Galaxy 2 have as much right to say they're at the center of the expansion? Yes. Can anyone claim to be a unique center of the expansion and hence center of the universe? No, because everyone is getting this. Okay. Last bit here. I know we're right at 4, but this should go real quick. We do a decelerating universe and an accelerating universe. So here's the distance versus time. We start by having them plot that. They use the dual feature. So here they replot the constant expansion. And then here's the one they're doing right now. And you can see it started faster and then slowed down to the current rate of expansion. So this is definitely a decelerating universe. And the pin positions are calculated as such. And they go through the process again. They get their D nows and D thens. And they plot it up. And the red one here is the constant rate of expansion. The blue one is the decelerating universe. And it curves upwards. And this makes sense because the farther away you're looking in the past. And in a decelerating universe, it was expanding faster in the past. So higher redshift in the past. And here in the present, it matches. But in the past, it had to be faster because it's decelerating. So it should curve up in a decelerating universe. And back 90s and before, everyone thought we must be living in a decelerating universe because all the matter, all the energy, the gravitational attraction is going to work against the expansion. Only inflationary theorists and people who measure ages of globular clusters said, no, that can't be because they're getting ages older than the cosmological age of the universe in a decelerating scenario. So we ask a basic question. Yes, it's curving up. So now let's do an accelerating universe. Again, they plot distance versus time of the pin position. And here's the constant. So it started out slower and over a longer amount of time speeds up. So accelerating universes give you older universes. And that's how we solve the problem of there are objects that had ages that were older than what people thought the universe was at the time. Anyway, they see, yes, this is an accelerating universe. They do it and it curves down in this case. The blue is the accelerating curving down compared to the constant. So then, as I said before, we show them the type 1a supernovae data with a constant expansion in the middle and one above and one below. They've now learned that if it curves down, that's accelerating. The data matches that one. So they conclude using type 1a's, which we haven't used yet. We've used our Lyraes and Cepheids in lab 6, but now type 1a's come back in. We live in an accelerating universe. We have them research and discuss dark energy. It's not the point of this lab. It's kind of the carrot. Like dark matter was the carrot of lab 7. Dark energy is the carrot of lab 8. And sources of error in the final minute. Accuracy with which the pins can be placed. Accuracy with which you can measure distances between stretched dots. As you stretch it, the dot gets stretched. These last two I don't believe, but I accept. Rubber bands stretch differently as they warm up. They stretch more easily, but I don't think the distances are any different, but I can't really prove it. 4, rubber bands do not always stretch uniformly. And that's probably true if the rubber band, when they laid it down, you had higher and lower densities, that it wouldn't stretch uniformly, but I imagine these things are manufactured pretty uniformly. So I accept those two, but I don't believe them. It's mostly about placing the pins and trying to measure the center to these stretched dots. 4 o'clock. Questions, thoughts?
Hey Dan, so I actually looked up on Google where does the energy go for cosmological redshift, and
Yes.
now like you get an AI result, but it does have some pretty reputable sources, but they pretty much just chalk it up to saying that energy goes into the expansion of the universe, which is
Yeah.
something that's not I'm really not comfortable with because you're basically saying that's like dark energy, right?
Yeah. Well, see, dark energy has the same problem in the opposite direction. As the universe expands, if it doubles in size, we have twice as much dark energy. Or I mean, if it doubles in volume, we have twice as much dark energy. Where'd that energy come from? And it doesn't equate to the light redshifting. Both of those, there's some mysterious reservoir of energy, and they say it's yeah, they say it goes into the expansion, but there's no term in the Friedman equation for this energy as it's being dumped. Um, I've read more about it, and they say it it's stored non-locally in the gravitational field. I'm not satisfied with that, but I'm not a general relativity expert, so it bothers me. One of the many things in modern physics that does. Well, anything else? Okay, if not, thanks. Next time will be our last time. We'll measure Hubble's constant and call it a semester. And now I better hurry up and reconcile my travel card, or else I can't travel ever again. So
Thank you,
see
Dan.
you all later.
Thank you.